We'll define a few words to begin with. The first word that we're going to define is systems of equations. Go ahead and highlight the phrase system of equations. A system of equations is two or more equations with the same variables. So just like those ones we just did had both hearts and diamonds in them when we were trying to figure out what they were worth, these are going to both have x's and y's, or a's and c's. Whatever we're going to use for our variables, they have to show up in both equations. It's a system of equations. Now, when we're finding a solution to these systems, which is the goal for today, not just writing them like we did last time, but actually solving them, we're going to be looking for the point of intersection. Okay, you did this last year. You found a spot where two lines crossed. That was called their point of intersection. So we can call this the point that they cross. That's called the point of intersection. Or the point that they touch or cross. Another definition we can use for a solution to a system is the x and y coordinate that makes both equations true. So just like the number that we used for the heart and the diamond had to be the same for both the top and the bottom equation, the x and y coordinate, if I were to plug them in, had to work in both the top and bottom equations. They have to make both of the equations true. Okay, to demonstrate this fact, we're actually going to do two problems, and we're going to do them out of order, because you're going to do number one by yourself here in a little bit with your group, but number two you're going to do with me right now. The question number two, the bottom one, says, which of the following is a solution to the system? Highlight or circle star underline the word solution. That word means we're looking for the x and y coordinate, which they gave me as answer choices, x and y coordinate. Which one of these, if I were to plug it into those equations, would come out true? So to organize my information, and since this is a multiple choice scenario, I'm going to make 4 grid-like areas on my notes just to organize myself. And I'm going to assign each of them a different letter so that I know which answer choice I'm working with in this grid. Okay. What we want to do, we want to know which of those x and y coordinates I could plug into the equation, plug in, and it would come out as a true statement for both equations. So if we look at the first one, we have the coordinate 2, -2. We want to plug that coordinate into both equations to see if it works. So let's try plugging it into the first one. This equation starts with y. So instead of writing y, what am I going to plug in? -2. So this is going to be -2 equal to -3 times x. But what are we going to plug in for x? 2. That's what we're substituting in. Minus 4. In your brain or in your calculator, you just figure this out. What is -3 times 2?
-6.
And -6 minus 4? -10. You could chunk this part in a calculator if you wanted to, but we're going to be using our brains today to do this. So -3 times 2 is -6. -6 minus 4 is -10. Is -2 equal to -10? No, these are not equal, so we're going to put a slash mark through our equal sign indicating not equal. Should I choose answer choice A? No, because it didn't work in one of them. It has to work in both. Let's try answer choice B. We do the same thing where we want to plug in our answers to see if it worked. We're going to start with that first equation. It says y, so what do I plug in? 2 equal to -3 times, substitute in x, -2 minus 4. We can calculate this in our brain or in our calculator. 2 equal to 6 minus 4. Well, what is 6 minus 4? Okay, good start. Can I call it done?
No, we have to do the other.
We do have to do the other equation. Guys, we have 2 equations now that it has to work for it to be a solution. So now we plug it into the second equation. Y goes first again, so this is going to be 2 equal to -2 plus 4. -2 plus 4 is still 2. So does 2 equal 2?
Yes.
I got 2 check marks. That means I'm pretty sure it's answer choice B, but I'm a good student, so I'm going to keep going and make sure that all the other answer choices are wrong. We try C. X and Y. Negative, go for it. Negative 1 equals?
Negative 3, 4. Plus 4 minus 4.
Minus 4. So negative 3 times 4 is negative 12. So we're going to see if negative 1 is equal to negative 12 minus 4. Well, guys, negative 12 minus 4 is negative 16. Is negative 1 equal to negative 16? No. So we say it is not equal to by putting a slash in our equal sign. Do we choose answer choice C? No. Cross that sucker out. We try D. How do you already know that? Yeah, if we plugged in 0, this would be 0 equal to negative 3 times 0 minus 4. Well, negative 3 times 0, that's 0. And 0 minus 4...
0.
For real?
No.
It's negative 4. 0 minus 4 is negative 4. So, is 0 equal to negative 4? No. We would still need to actually do the x and y plugging in. You can't just say that 0, 0 isn't right. Sometimes it might be my solution. So, don't just like cross it out just because. We only have one answer choice left, so we would know that answer choice B is our solution. We feel very confidently that that's going to be where these two lines intersect, because we have plugged in our answers, made sure that they make the equation true. Now, we are going to have you guys be responsible for number 1, but here's how we're going to do it to expedite the process. If you are sitting in a desk and your desk is labeled with a number 1, you're going to check answer choice A. If you're sitting at a desk labeled number 2, you're going to check answer choice B. 3, you have C, and 4, you have D. You're just plugging in that one answer choice, and then as a team, you're going to be able to find the answer. Does everyone know what we're doing? Okay, go for it. So after we do all of the work, we know answer choice D is correct. All right, so the first of 3 methods that I said the first of 3 methods, and I only held up one finger. The first of 3 methods that we're going to be using to solve our systems is called graphing, which we all kind of know what's going to happen here. Now, we're going to be graphing lines and systems today to try to find their intersection point or find their solution. Before we do that, though, we need to talk about the types of solutions you may see when we graph these equations. Okay, the first one's right here. We defined earlier that the solution is the point of intersection. How many points of intersection are parallel lines going to have?
0.
0, because they're like parallel. So are they ever going to touch?
No.
No. So parallel lines that have the same slope, are going to have no solution, because they will just like not cross. Now this one, how many solutions does it have? 1. There's one intersection point right there in the center. We're not talking about what it is just yet, but we are going to talk about the fact that there is one solution. This is a type of solution we might see, because it crosses one time. We're going to be able to give it an answer. This is the majority of the questions you'll see. These other 2 are called special cases. But if we look over here, it says it's the same line. So what happened is they graphed the blue line, and then they graphed the red line, and it showed up right on top of it because they are the same. Now, we said that the solution is the point of intersection. How many times do lines graphed right on top of each other have the same intersection point?
Always.
Yeah, they have it like here and then there and there and there and there and there. You know, if I could just like dot along the whole thing, they'd all be intersection points, right? So what's the math phrase we use?
Infinitely many solutions.
Infinitely many solutions. Awesome. Infinitely. Oop, I spelled that wrong. That's embarrassing. Many solutions. Now, I told you all year long, mathematicians are lazy. After you write the infinitely many solutions once, you can always write IMS. I'm totally down for IMS as how you write this. But just make sure if you see infinitely many solutions written down, you know that's what you mean by IMS. Okay? Deal? I accept IMS if you at least know what it translates to. Now, there are arm motions for all of these types of solutions. Now, remember, I'm not asking you what are the solutions. I'm asking you how many. So if I'm asking you to show me the arm motion for no solution, you're going to hold up 2 parallel lines with your arms. So they're just up in front of your face. So everybody hold up no solutions. Let me see your arms in the air. No solutions. How many solutions does this one have?
1.
one solution. So if you cross your arms in front of you, your arms have crossed once. Now this is kind of hard to do in this jacket because my arms are not that flexible anymore. But if you try to make the same line with your arms, so try to get them right on top of each other. Yeah, y'all are better at this than me. How many solutions does this have?
Infinitely many.
Infinitely many solutions. So very quickly, if I hold up my arms, y'all yell at me how many solutions this have. Are you ready?
No. One. Infinitely.
Zero.
Oh, no.
Gotcha.
Infinitely many. One. None. One. None. Infinitely many. One.
Okay, you get the idea. We're gonna take a second. It's really hard to do the infinitely many. Like my jacket is like real tight on my back. We're gonna take a second. We're gonna play a game really fast. All right, so that was pretty fun. So let's take what we learned by playing that game with our friends here, and let's answer these questions. Questions 1 through 4 don't ask me to find the solution. They ask me how many solutions. So this is just like the game we played around the room. How many solutions does this graph have? One solution. Very good. How many solutions does this graph have?
Infinite.
Infinitely many solutions. Very good, because they're the same line. They are right on top of each other. How many solutions does this one have? No solutions. What's up? Okay. Now, if we look at this last one, they didn't give me a picture, but what do you notice about these two equations?
They're not the same.
They're not exactly the same.
No.
But they both have it. First base, 2.
They both have a 2 right here, which means
That's their
what is
slope.
the same? And it's their slope. So if they have the same slope but a different y-intercept, they're not the same line.
Parallel.
They're parallel to each other. So what is this? How many? Yeah, I hear you. These are no solutions. Now let's say like maybe we forgot or we're like, ooh, I can't remember if that's no solution or infinitely many. There is a way for us to check our work. Okay, you can check this in your calculator because we just want to graph it and see what it looks like, or you can use the fun, free, and cute website and or app called Desmos that you have open on your computers. So right now I would like for you to graph both the top and bottom equation at the same time on your screen to see what they look like, because it will help you see and make sure you remember how many solutions that it has. Now I can't show Desmos on the screen at the same time as this, so I'm going to have to cut over to it here to show you. So using Desmos to visually see what's happening here will help you remember, especially since we're such visual people. Okay, now the whole gist of today is not just to tell me how many solutions something has, although that's really fun to do all the hand signs. We also need to tell me what is the solution to the system. Well, those steps right here and the little dotted outburst are going to be what we do for the rest of class. The steps to find an actual solution are to graph each equation on the same coordinate grid, kind of like we just did on our Desmos, like put them on the same graph. Then we're going to estimate the point of intersection, because we're going to be doing these by hand. So we're going to estimate where we're pretty sure they cross, but we're human, so we make errors. So we're always going to check our solution by either plugging back in the x and y we got, like the beginning of the notes, checking if they make both equations true, or using our Desmos to help us out and double check our graphing. Okay, so we're going to graph it and find the point of intersection. This is going to be a semi-review of graphing, which we did a while ago. So let's see what we remember. When you've got this all written down, go to the inside of the notes to number 1. Go to the inside of the notes to number 1. Notice the prompt has changed. It doesn't say how many solutions anymore. It says, what is the solution? This time we're going to have to give an x and y coordinate answer that explains where on that coordinate grid these two lines cross, because that's what is the solution. Okay, so if we look at number 5, the first equation in number 5, we need the slope and we need the y-intercept. What is the slope of number 5? 1/2. We're going to circle the slope because we did that on our quiz today. We're going to circle the slope. We're going to box the y-intercept. What is the y-intercept here? 2. Positive 2. Now, I'm going to do this on the screen. You got to help me out. Did I begin correctly?
No.
Oh, what did I just do wrong?
You started on the x-axis.
Yeah, you started on the x.
And what is that b value called?
Y.
The y-intercept. Oh, snap. So I have to start over here at 2. And then to create more points to graph this line, what do I do to find more points? I use the slope. How? Rise over run. So from the point I just graphed, we're going to go up how many?
1.
And over how many?
2.
Always to the right. What direction?
To the right.
Thank you. We're going to go up and to the right again. Up 1 and over 2. Until I think I can draw a pretty good straight line in between these points.
Hold on.
Okay? Use your ruler to draw a straight line through the points. Oh, that's not straight. Try again, Miss Quigley. Now, am I finished? No, because we have a system of equations. That's how many equations?
2.
Two or more. So we are also going to have to graph the second one at the same time to be able to see where they cross. What's the slope of the second line? Negative 1/2. So I want you, once you've got that other one graphed, I want you to circle the slope of the second equation. And I want you to box the y-intercept. What's the y-intercept of the second equation? 4. Okay? Now I know where to begin, and I know how to move. Did I begin correctly?
No.
Oh, I did it again. This is called the y-intercept, not the x-intercept. So I'm going to start at 4. Then to create more points, how am I going to move? Down.
Rise over run.
It's going to rise over run, so I'm going to go down
1.
and to the right 2. So always to the right. So I'm going to go down 1, right 2. Put a dot. Down run 1, right 2. Until I feel like I can make a straight line. 3 or 4, maybe 5 points is appropriate, but we're going to run out of space if we do more, so 3 is fine. Then I use my straight edge or my ruler to make a really nice straight line in between those points. We have successfully graphed this system of equations. But I asked you not how many solutions, I asked you what it is. So where does this coordinate exist that puts these two lines together? Where do they touch?
2, 3.
2, 3. Okay, 2, 3 is my solution because that's the coordinate where these two things cross. We go side to side and then up and down for coordinates. Gotta run before you get, I don't know, side to side, up and down. Now, let's say we weren't 100% sure that we graphed this correctly, because sometimes we're going to have some crazy graphs that we're doing. We want to make sure that we're correct. How do you guys think we could make sure we're correct on this practice problem?
So I need to log it into Desmos.
We could totally do in Desmos. We could graph those two lines and see if that's where they cross. We could also plug in the x and y coordinate back into both equations to make sure it's true. You pick your poison. You decide how you're going to check your work. I'm going to personally check it with Desmos because I want to check my graphing skills. So we're going to pop over to Desmos. So we just checked it in Desmos to make sure that 2, 3 is what the point of intersection is. You guys are going to practice on number 6. Okay, before we start on number 6 where I let you go, we are going to talk about the slope and the intercept here. What's the slope of the first line?
The slope of 2.
The slope of the first problem on number 6 is 2/3. What's the y-intercept of that problem?
0.
How did you know that?
It's not there.
Absolutely. If nothing's there, thank you, we're going to know that it's plus 0. What's the slope of the second line?
1 over 1.
1 over 1 because the coefficient of x, when it's invisible, is 1, and 1 as a fraction is 1 over 1. What's the y-intercept of the second equation?
Negative 1.
Of the second equation?
No.
Thank you, -1. Okay, with that information, I want you guys to practice graphing. Think back to how we graphed. The y-intercept is where you begin, the slope is how you move, and you can always check your work with Desmos. I'll let you think. Okay, I know I might be cutting off your thinking here, but I'm gonna keep rolling here. Finish if you're ahead of me. The first equation begins at 0 and has a rise of 2, run of 3. A rise of 2 and a run of 3. Oop, kind of off the graph, but good enough. So we're going to draw our straight line in between all of these points. there's my graph for the first equation. The second equation begins at -1, goes up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. I feel good. I can draw my line now. So I connect those dots together across the entire graph, and I look for the point of intersection. Where do these two lines intersect? 3, 2. The coordinate where they intersect, the point of intersection, is the solution. So these two lines intersect or both appear at 3, 2. Did you guys check it on Desmos to make sure we were correct?
Yes.
Sweet. When we do that, we notice the following. All right, we'll look at the 7th question here. Is this 7th question in a form where we can find the slope and y-intercept right away? No, but guess what we practiced earlier today that we can do? What did we practice at the end of the quiz?
Y.
Yep, what's that called?
Solving for Y.
Solving for y or isolating the y. By doing that, we'll have it written in y equals mx plus b form. So let's do that really quickly for both questions. If I have the first one, minus 3x plus 2y equal to -6, and I want to move the x to the other side, what am I going to use?
Inverse operator.
Correct, which is
3x.
positive 3x on both sides. I use positive 3x because that cancels out the negative 3x. And I'm left with 2y equal to positive 3x minus 6. Am I finished solving for y?
No.
No, what do I need to do next?
Divide by Y.
Divide by 2. This would be y equal to 3/2 x minus 3. So there's the first equation written in the format where I know how to graph it. We just need to do the second one. The second one is 2x minus y equal to 3. What do I move first? The x term by doing what? How do I move that x term? What's the inverse or the opposite of what's already there?
Negative.
I'll subtract 2x from both sides. It's the opposite of what's already there. It's its inverse operation. This would be negative y equal to negative 2x plus 3. Am I finished? No, what do I need to divide by? -1, thank you. Awesome, great, you rock. Sorry. This would be y equal to 2x minus 3. Okay, now that we have them solved for y, they're in y equals mx plus b or slope-intercept form, and we can graph them. I'm going to pause for a second and give you time to graph on your paper and check with Desmos. Accuracy is key here. Okay, sorry if I'm cutting off your thinking, but we're going to roll on. The first one, its slope is 3 over 2, and its y-intercept is -3. So from -3, I'm going to go up 3 over 2, up 3 over 2, until I can draw a straight line in between those 2 points. The second equation, when we solved it, has a slope of what?
3 over 2.
The second one, sorry. The second one. 2 over 1. Cool. And what's its y-intercept?
-3.
So it's going to begin at -3 as well, and it's going to go up 2 over 1. Up 2 over 1. Up 2 over 1.
Oh, that's almost away, Cameron. It is.
What were we going to say? It almost looks like it was going to be right on top of each other, right? Just has a different slope, but it had the same y-intercept. So where's the coordinate where they intersect? What's its solution? 0, -3 is my solution. That's where they both cross. Now this one is kind of rough because even my graph right there, using my ruler, it looks like there's almost 2 points where they intersect. So I super want to check and make sure that this one is correct in my Desmos. Fun fact though, Desmos is smart enough that it can graph standard form functions unlike your calculator. The calculators that we have can only graph y = mx + b formatted questions, but Desmos, along with some other calculators that we don't have, can graph those standard form functions. So you wouldn't even have to change it into y = mx + b to use Desmos. Let me show you. We're going to combine now what we did last class with what we've learned this class. So we're going to take a real world scenario, this problem over here, and we're going to write a system of equations or 2 equations that represent this scenario, and we're going to graph them and figure out what the solution is. So if we read, it says 2 customers went to a post office to buy postcards and large envelopes. Each postcard costs the same amount, and each large envelope costs the same amount. The first customer paid $4 for 2 postcards and 1 large envelope. The second customer paid $8 for 6 postcards and 1 large envelope. What is the cost in dollars of each postcard and each large envelope? All right, this is what the question would say. Your STAR test, your teacher test, whenever I give you a quiz question, it's just going to say this. All of these other parts are things you're going to need to know how to do to get you to the final answer. They're not always going to be broken down step by step for you. You have to know that all parts A through D are something you have to do to actually answer that question. So we start with A. It says to define your variables. What variables, what things are we talking about in this question? The cost of postcards and the cost of large envelopes. Cost of postcards is what we don't know, but it's what we're talking about. And the cost of envelopes is what we don't know, but it's what we're talking about. We reread the question. It says the first customer paid $4 for 2 postcards and 1 large envelope. Okay, so let's put an equation together for the first customer. They had 2 postcards. So 2 goes next to which letter? X, because that's my postcard. That's what I decided would be representing my postcards. And how many envelopes? 1 envelope. If you want to put the 1 there to show that there's a 1 in front of the Y, that's cool. You don't need the 1. And how much money did the first customer spend? 4. Now you're probably wondering, Miss Quigley, last time you told me money plus money has to equal money. Well, our variables themselves are representing a money number. So this is still money plus money equal money. It just happens to be that our variables are talking about the money this time. Our second customer, it says that they paid $8 for 6 postcards and 1 large envelope. So not 8x, but what goes with the postcards? 6x and 1 large envelope, $8. Now, we are going to use Desmos on this question to help us graph it. We're still going to have to graph it accurately by hand. I want you to use these 2 equations to get the intercepts and graph them. If you find the intercepts using Desmos, we're going to be able to fill in this graph right here and find by hand what the solution is. So I'm going to pop over to Desmos for a second. This one should cross at 4 and 2, 4 on the y-axis and 2 on the x-axis. Thank you, Desmos, for the intercepts. Now that I have the intercepts, I can graph the line in between them, being as accurate as possible. And I go back to Desmos to find the intercepts of the second equation. I put 1.33 already on there for you because I knew it was going to be our intercept and it was going to be a decimal / fraction. So we know the y-intercept was at 8 and the x-intercept is at 1.33. Thank you, Desmos. We can graph them, draw a line between them, and graph our equation.
Wow.
And now that we've hand graphed this on our paper, / I'm pretty sure all of you guys are looking at it on your Desmos right now to begin with, where is the solution?
1, 2,
At the coordinate
1, 2.
1, 2, which is right there. Did you guys see that open up on Desmos, that when you typed them both in, the intersection point came up?
Yup.
Cool. So we have our intersection point. Now we're not done though, because this question didn't ask me for the coordinate of the solution. It asked me, actually, if you reread the question, it asked me what was the cost in dollars of each postcard and large envelope. Well, if this is the solution set, what does this coordinate 1, 2 tell me about postcards and envelopes?
The price.
We said that X was representing what?
The cost of postcard.
So how much is a postcard?
$1.
$1. How much is an envelope?
$2.
$2. That's why we have to label our stuff, because we're going to forget what's what. So by labeling it, we know that each postcard costs $1, and each envelope costs $2. We just solved a real world problem, because for some reason this post office doesn't have their prices labeled. I don't know.
You crazy.
Right? Crazy post office. What are you thinking? Do I have any last minute questions before we're done with notes?
It was $2.
All right.